Hello, everyone. I hope you're doing well. I'm Meher Dudeja, and today I'll be presenting my research on Diophantine triples. So let's start. So this research has been done under the guidance of Professor Aklilu Zelecki. He is in joint appointment with Lyman Briggs College and Department of Statistics of Michigan State University. This research has been funded by Lyman Briggs College Research Fund, and I thank them for believing in me and my research. So let's talk about what are Diophantine triples. So let's assume that you have a set of three numbers, A, B, and C. The permutations of the multiples is A multiplied with B, B multiplied with C, and C multiplied with A. Now we say that this triple is a d-Diophantine triple if you add the constant d to this multiple and if it is a perfect square. Like here, a multiplied with b and I added d, and if it is a perfect square, that means k has to be a whole number. Now, in this direction, in this research project, we had a look over recurrence series, how we can generate infinite Diophantine triples. And for the purposes of this research, the d constant is 1. For the first recurrence series, we start with a very well-known recurrence series of 138. Now, 138 is a Diophantine triple because if you multiply 3 with 1, you add 1, it's 4, which is a perfect square. And we decided to name it class 1 because, it starts with 1. And a generalized formula is 1, Bn, and Cn, as you can see. Now, the Python using a Python code, I found that the sequence is basically 3, 8, 15, 24. The formula is Bn is equals to n squared minus 1, and Cn is equals to n squared plus 2n. If you were to closely notice it, n squared plus 2n is nothing but n plus 1 whole square minus 1, which basically means that your Cn is the next term of the series. Now, the proof. Here's a proof that we did with the algebra. Now, if you multiply it with if you multiply bn with 1 and you add 1, it's a perfect square because n is equals to k. Then for the next one, if you do, calculations, you get n plus 1. And for the last one, if you multiply bn with cn, you get n squared plus n minus 1 whole square. So that means this series is a recurrent series, which is also a Diophantine triple. Now, I was interested to see where is this leading to. The asymptotic behavior of this recurrence is also very interesting. Also very interesting. What I mean by asymptotic behavior is that if you put t is equals to infinity, right? What is the change? What is the prospective change in the behavior or the ratio of the two, of the Cn and the Bn terms, because they are the ones that are varying, right? Now, you can see, putting that as at infinity, we get that the recurrence series tends to 1, like the ratio becomes 1. So at a certain point, those two numbers are kind of equal at infinity. Now, if you see, that's how the graph of this asymptotic behavior looks like. The second recurrence series, all I did was modify my Python code so that the first term is 2. And that revealed another recurrence series, which was 4, 12, 24, 60, and also in the middle 40. So this is the second recurrence series. So the formula is 2n squared plus 2n, and Cn is 2n squared plus 6n plus 4. If you were to closely notice this again, basically your Cn is the next term of the series. It's basically 2n plus 1 and n plus 2. Again, we perform the algebra on it to prove that it is a Diophantine triple. You see, they all become perfect squares, with the first one being 2n plus 1, the second one being 2n plus 3, and the third one being 2n squared plus 4n plus 1. Now, the second recurrence series also have the same asymptotic behavior as the previous one. It tends to 1, as you can see in the graph. So we tried to extend this property of triples of Diophantines to D-Diophantine quadruples. The definition is that we basically extend the quadruple to A, B, C, E, the fourth term, and the permutations multiply, because previously we had 3 permutations, now we have 6 permutations. This is A, B, B, C, C, A, E, A, E, B, and E, C. Now, all of those have to be a perfect square after you add D, of course. D in this case also is 1. Now, using the Python code, I extended the property using the first recurrence series formula, which was n squared minus 1. So the first term, which is actually a very well-known quadruple, is 138,120. However, the second term I found was 18120 and 4095. Unfortunately, we cannot find a third term. We are en route to do some analysis. Why isn't there a third term? Our hypothesis is it does not exist because the computer has not revealed any number. I tried to analyze these terms. If you see that 138 is basically 1, T2, T3, T11, and then you have T3, T11, and T64. However, we cannot find the next term, and that's actually one of the future goals of this project. The second recurrence series also has a Diophantine quadruple, which is 2, 4, 12, 420, and then you have 2, 12, 420, 41,184, which are T1, T2, T3, T14, and T3, T14, and T143. In this direction also, we could not find a third term, unfortunately, but that's a future goal. So the future goal is right now the third recurrence series is in works. It seems that it has 2 independent branches. So as you saw that in class 1, you had just one branch. In class 2, you had just one branch, a well-defined formulas, and, there's just one branch. In 3, however, there seems to be 2 independent branches which never intersect. They have different formulas. And based on this, we have a hypothesis running that if you go further, like let's say if I try to find of class 4, the number of branches would be 3. This is basically growing at a Fibonacci rate. That's our hypothesis, but that's for the future of this project. And of course, we'll try to work with quadruples to see if there exists any formula or something that we can use to predict the third term. If not, we'll try to come up with a proof that the third term cannot exist. Again, I would like to extend my thanks to Professor Aklilio Zelecki for his constant help and working with me. And again, this research was funded by Lyman Briggs College, a research fund. I thank them very much. And also, I would like to extend a special thanks to my friend Curtis Chow and Amiri Walker for the constant support. Thank you. Have a good day.